Hello and welcome. Tonight we are going to explore one of the strangest invisible forces in the universe. A force that can turn a compass needle without touching it. A force that can lift heavy metal from the ground. A force that spins motors, powers generators, guides particles through space, protects Earth from the sun, paints auroras across polar skies, and reaches into some of the most extreme places in the cosmos. It is silent. It is invisible. It has no smell, no color, no weight you can feel in your hand. And yet it is everywhere, around magnets, inside wires, deep beneath Earth's crust, in the boiling surface of the sun, between planets, inside galaxies, and around dead stars so powerful that their magnetic fields could distort atoms themselves. This force is magnetism, and the shape it creates around itself is called a magnetic field. At first, a magnetic field seems almost like magic. Place a compass on a table, and the needle turns toward north. No hand pushes it, no string pulls it, no visible current of air moves it. It simply responds to something hidden in the space around it. Hold a magnet near iron filings, and the tiny pieces arrange themselves into graceful curves, as if they are obeying invisible roads. Bring two magnets close together, and they may snap toward each other with sudden force. Turn one around, and they push apart, refusing to meet. Nothing visible stands between them, and yet the force is real. The question is simple. How? How can something invisible reach through empty space? How can a magnet pull iron without touching it? Why does a compass know where north is? Why do electric currents create magnetism? Why does Earth have a magnetic shield? And why does the same hidden force appear in machines, planets, stars, and galaxies? To understand magnetic fields, we have to begin with something that feels very ordinary, but is actually deeply strange. Space is not empty in the way it first appears. A room may look empty. The air may be still. A patch of space between two magnets may seem to contain nothing at all. But physics tells us that space can hold conditions. Space can have temperature. Space can have pressure. Space can have gravity. Space can have electric fields. And space can have magnetic fields. A field is a way of saying that every point in space has some kind of hidden instruction. If you place an object there, something will happen. In a gravitational field, a mass feels a pull. In an electric field, a charge feels a force. In a magnetic field, moving charges and magnetic materials feel a twist, a push, or a pull. A field is not a solid object. It is not a wire, a string, or a fluid. It is more like an invisible map, a map of influence, a map that tells matter how to move. This is the first step into the mystery. A magnet does not need to touch another object because the magnet changes the space around it. It fills that space with a magnetic field. The field reaches outward. It curves. It weakens with distance. It has direction. And when something sensitive to magnetism enters that field, it responds. The response can be gentle, like a compass needle turning, or sudden, like a magnet snapping onto metal. The field was already there. The object simply revealed it. One of the oldest and most beautiful ways to see a magnetic field is with iron filings. Place a bar magnet beneath a sheet of paper. Sprinkle iron filings on top. Tap the paper gently. The filings shift and rotate, forming curved patterns around the magnet. They gather near the ends. They sweep outward from one side and curve back toward the other. It looks like the magnet is surrounded by invisible lines. These are called magnetic field lines. But the lines are not physical strings. They are a way to draw the field. They show the direction a compass would point. They show where the field is stronger. Where the lines are close together, the magnetic field is stronger. Where the lines spread apart, the field is weaker. This is why the ends of a magnet feel strongest. The field is concentrated there. We call those ends the North Pole and the South Pole. Opposite poles attract, like poles repel. North is drawn to south. North pushes away north. South pushes away south. This rule is familiar, but it hides something important. No one has ever found an isolated north magnetic pole or an isolated south magnetic pole in ordinary nature. If you cut a bar magnet in half, you do not get a separate north piece and a separate south piece. You get two smaller magnets, each has its own north and south pole. Cut those pieces again, and the same thing happens. North and south remain paired. Magnetic fields form loops. They do not begin and end in the simple way electric fields can begin on positive charge and end on negative charge. Magnetism curves back on itself. It is a force of loops, rotations, and hidden circulation. That is why magnets feel so mysterious. Their field seems to pour out of one end and return to the other, but deeper down, the magnetic field is part of a looped structure. It curls through space, it surrounds moving electric charge. And this brings us to the deeper truth. Magnetism and electricity are not separate forces. They are two faces of one larger force, electromagnetism. At first, electricity and magnetism seem different. Electricity makes sparks, lightning, batteries, currents, and shocks. Magnetism makes compass needles turn and iron stick to magnets. But when scientists studied them carefully, they discovered that the two are connected. An electric current creates a magnetic field. A changing magnetic field can create an electric current. A changing electric field can create a magnetic field. A changing magnetic field can create an electric field. Together, they form one of the fundamental forces of nature. This connection is not a small detail. It is one of the foundations of modern civilization. Every electric motor depends on it. Every generator depends on it. Every transformer in the power grid depends on it. Every radio wave, microwave, and beam of light depends on it. Light itself is an electromagnetic wave, a traveling pattern of electric and magnetic fields moving through space. When you see the glow of a lamp, the color of a sunset, the stars in the sky, or the screen in front of you, you are experiencing electromagnetism. The same family of forces that makes a magnet stick to a refrigerator also lets light cross the universe. That is the scale of this idea. From a compass needle on a table to starlight traveling across galaxies. But where does a magnetic field actually come from? The simplest answer is this. Moving electric charges create magnetic fields. Electric charge at rest creates an electric field. Electric charge in motion creates a magnetic field. In a wire, countless electrons move together as an electric current. Around that current, a magnetic field forms. The field circles around the wire, wrapping it in invisible loops. If the current grows stronger, the magnetic field grows stronger. If the current reverses direction, the magnetic field reverses direction. If the wire is shaped into a coil, the magnetic fields from each loop add together, creating a stronger field through the center. This is the basic idea behind an electromagnet. A magnet made from electricity. Turn the current on, and the magnetic field appears. Turn the current off, and the field fades away. This is already powerful, but place iron inside the coil, and the field can become much stronger. That is because iron is a special kind of material. Inside it, there are countless tiny magnetic regions called domains. Each domain acts a little like a small magnet. In ordinary iron, these domains often point in different directions. One points left, another points right, another points upward, another points downward. Their effects mostly cancel out. So the whole piece of iron may not behave like a strong magnet. But if many domains line up in the same direction, the iron becomes magnetized. The tiny magnetic effects add together. The material gains a strong north and south pole. It becomes a magnet. This is why some materials are magnetic and others are not. Iron, nickel, cobalt, and some special alloys can form strong magnets because their internal magnetic domains can align. Other materials do not behave this way or only respond weakly. A permanent magnet is not powered by a battery. It does not need a visible current through a wire. Its magnetism comes from the alignment of tiny magnetic effects inside the material, rooted in the behavior of electrons and their quantum properties. Here, the story becomes stranger. At the deepest level, magnetism is not only about electrons moving through wires. Electrons themselves have a kind of built-in magnetic character. This property is called spin. Though it is not exactly like a tiny ball spinning in the ordinary sense, it is a quantum property, one of those features of nature that has no perfect everyday comparison. Because of spin and the way electrons move around atoms, atoms can have tiny magnetic moments. In most materials, these tiny effects point in random directions and cancel out. But in magnetic materials, they can line up. And when they line up, something large emerges from something tiny. A magnet you can hold in your hand is the result of countless microscopic magnetic effects acting together. A hidden order inside matter creates a field outside matter. This is one of the most beautiful patterns in physics. Small alignment creates large influence. Tiny arrows inside a material become invisible curves in space. Now think about a simple fridge magnet. It seems ordinary, almost boring. But inside it, billions upon billions of tiny magnetic effects are arranged in such a way that the magnet changes the space around itself. It reaches outward, it pulls on metal, it holds a note to a refrigerator door. The act is small, the principle is cosmic. The same laws that hold that note in place also help drive electric motors, protect planets, and power storms on the sun. Electromagnets reveal the practical side of magnetism. Imagine a coil of wire. Current flows through it. A magnetic field forms. Place another magnet nearby, and the two fields interact. One pushes, one pulls. The coil turns. That is the basic idea of an electric motor. Electricity becomes motion. This simple transformation changed the world. Fans spin. Trains move, hard drives operate, washing machines turn, elevators rise, electric cars accelerate, speakers vibrate, power tools cut and drill, factories run. Almost everywhere electricity becomes movement, magnetic fields are involved. But the opposite is also true. Motion can become electricity. Move a magnet near a coil of wire and an electric current can appear. Move a coil through a magnetic field and current can flow. This is electromagnetic induction. It is the principle behind generators. A generator uses motion and magnetic fields to create electricity. In a hydroelectric dam, falling water turns turbines. In a wind turbine, moving air turns blades. In a power plant, steam turns machinery. In each case, motion is used to move magnetic fields and coils relative to each other, producing electric current. This is one of the great hidden engines of modern life. A magnetic field lets us turn motion into electricity, and electricity into motion. Without that connection, the modern world would look completely different. Power grids would not work the same way. Electric motors would not fill our homes and cities. Communication technologies would not exist as we know them. Magnetism is not just a curiosity. It is built into civilization. It is inside the walls, inside machines, inside hospitals, inside transport, inside the invisible systems that keep modern life moving. In a hospital, magnetic fields become even more remarkable. An MRI machine uses powerful magnetic fields and radio waves to create images inside the human body. It does not cut the body open. It does not need visible light. Instead, it uses the magnetic properties of atomic nuclei, especially hydrogen and water and fat, to build detailed images of soft tissues. A person lies inside a strong magnetic field. The nuclei inside the body respond. Radio waves are sent in. signals come back. A computer turns those signals into images. The same force that moves compass needles can help doctors see inside the brain, spine, heart, joints, and organs. Magnetism becomes medicine. A quiet, invisible field becomes a map of life. But to understand why magnetic fields feel so universal, we must leave machines behind and go deeper, beneath our feet. Earth itself has a magnetic field. A compass needle turns because Earth behaves in a rough way, like a giant magnet. The magnetic field extends far into space, forming a protective region around our planet called the magnetosphere. But Earth is not magnetic because there is a giant bar magnet hidden inside it. That would not work. Earth's interior is far too hot for ordinary permanent magnetism to survive. Instead, Earth's magnetic field is generated by motion deep inside the planet, beneath the crust, beneath the mantle, in the liquid outer core. There, molten iron and nickel move in slow, powerful currents. The planet rotates, heat flows outward, conductive fluid moves, electric currents form. Those currents create magnetic fields. The magnetic fields influence the motion of the fluid. Together, the process sustains Earth's magnetic field. This is called the geodynamo. It is one of the quiet miracles beneath our world. Deep inside Earth, in darkness, liquid metal flows, and from that motion, an invisible shield rises into space. Earth's magnetic field is not perfectly stable. It drifts. It changes. The magnetic North Pole moves. Over long timescales, Earth's magnetic field can weaken, strengthen, and even reverse, with north and south magnetic poles switching places. These reversals have happened many times in Earth's history. They are recorded in rocks, especially in volcanic rocks and seafloor crust, where magnetic minerals preserve the direction of Earth's field when they cool. The planet remembers its magnetic past, not in writing, not in fossils, but in stone. Earth's field matters because the sun is not quiet. The sun constantly sends charged particles into space. This stream is called the solar wind. Without a magnetic field, more of those charged particles could interact directly with Earth's upper atmosphere. Earth's magnetosphere helps deflect and guide many of them. It does not make Earth invulnerable, but it helps protect the atmosphere and the surface environment. It also creates one of the most beautiful sights on Earth, auroras, the northern and southern lights. When charged particles from the sun interact with Earth's magnetic field, many are guided toward polar regions. There, high above the ground, they collide with atoms and molecules in the atmosphere. Oxygen glows green and red. Nitrogen can glow blue, purple, and pink. The sky becomes a curtain of light. Waves, ribbons, arcs, shimmering veils. Auroras are not just pretty lights. They are magnetic fields made visible. They are the sky showing us the shape of invisible forces. For most of the time, Earth's magnetic field cannot be seen. But during auroras, its influence appears as color. The invisible becomes luminous. The hidden shield becomes art. And the story does not stop at Earth. Other planets have magnetic fields too. Jupiter has the largest and most powerful planetary magnetic field in the solar system. It is enormous, stretching millions of kilometers into space. It traps charged particles and creates intense radiation belts. Its magnetic environment interacts with its moons, especially Io, a volcanically active moon that feeds material into Jupiter's magnetosphere. Mercury, despite being small, has a weak global magnetic field. Mars does not have a strong global magnetic field today, though parts of its crust preserve ancient magnetism, suggesting it may have had a stronger field in the past. Venus lacks a strong global magnetic field like Earth's, even though it is similar in size to our planet. Why do some planets have magnetic fields and others do not? The answer depends on their interiors. A planet usually needs a conductive fluid region, internal heat, motion, and rotation. It needs a dynamo. If the interior cools too much, if the conductive layers stop moving in the right way, or if the internal structure is different, the global magnetic field may fade. This matters for habitability. A magnetic field is not the only thing that makes a planet habitable, but it can help protect an atmosphere from solar particles over long periods of time. It can shape how a planet interacts with its star. It can influence radiation near the surface and upper atmosphere. Magnetism is part of the planetary story, not the whole story, but an important hidden layer. A world is not only rock, air, water, and light. It may also be wrapped in a field that can protect, a field that can vanish, a field that can change the fate of a planet over deep time. Now look toward the Sun. The Sun's magnetic field is complex and restless. It twists, it loops, it emerges through the surface. It creates sunspots, darker regions where strong magnetic fields affect the flow of heat. It stores energy in curved magnetic structures. And sometimes those structures snap and reconnect, releasing enormous bursts of energy. This process is called magnetic reconnection. It can power solar flares. It can help launch coronal mass ejections, huge eruptions of plasma and magnetic field into space. When these eruptions are directed toward Earth, they can cause geomagnetic storms. The result can be beautiful auroras, but it can also affect satellites, radio communication, GPS, spacecraft, and even power grids. In space, magnetic fields are not quiet decorations. They are active. They can store energy. They can release energy. They can accelerate particles. They can shape storms larger than planets. A solar storm is not just hot gas flying outward. It is magnetized plasma moving through the solar system. The Sun throws magnetic weather into space. Earth receives it. Our magnetic field responds. The sky glows. Technology trembles. And once again, invisible fields become visible through their effects. This is why scientists study space weather. Because magnetic storms from the Sun can affect the technological systems we depend on. Satellites can be damaged. Astronauts can face increased radiation risk. High-frequency radio can be disrupted. Power grids can experience induced currents. Pipelines and cables can be affected. The modern world is electrical, and because electricity and magnetism are connected, the modern world is vulnerable to magnetic storms. The same invisible force that helps civilization function can also disturb it. The Sun teaches us that magnetic fields can be gentle and violent. They can guide auroras. They can erupt with power. They can be beautiful. They can be dangerous. Now travel farther. Beyond the planets, beyond the solar wind, into the space between stars. Even there, magnetic fields exist. Interstellar space is not truly empty. It contains gas, dust, cosmic rays, radiation, and magnetic fields. These fields are weak compared with a fridge magnet or Earth's field, but they stretch across enormous distances. In nebulae, magnetic fields can influence the movement of gas. In star-forming regions, they can affect how clouds collapse. In galaxies, magnetic fields thread through spiral arms and interstellar space, guiding charged particles and helping shape cosmic structures in subtle ways. A galactic magnetic field is incredibly faint by everyday standards. You would not feel it. It would not pull a nail from your hand. But across thousands of light years, even weak fields matter. The universe is full of plasma, charged particles, and motion. Where charges move, magnetic fields appear. Where magnetic fields change, electric fields appear. Together, they shape much of the visible universe. They are in the solar wind, in nebulae, in jets from black holes, in the disks around young stars, in the remnants of supernovae, in the vast spaces between galaxies. Magnetism is not local, it is cosmic. But the most extreme magnetic fields we know are not found on Earth or around ordinary stars or even in most galaxies. They are found around a special kind of dead star, a neutron star. When a massive star reaches the end of its life, it can explode as a supernova. Its outer layers are blasted into space, while its core collapses inward. If the remaining core is not massive enough to become a black hole, it may become a neutron star. A neutron star is incredibly dense. It can contain more mass than the Sun compressed into a sphere only about the size of a city. Matter inside it is crushed to extremes beyond ordinary experience. A teaspoon of neutron star material would have an unimaginable mass on Earth. Some neutron stars rotate rapidly. Some emit beams of radiation, like cosmic lighthouses. Some have powerful magnetic fields. And some have magnetic fields so strong that they form a class of objects called magnetars. A magnetar is a neutron star with an extreme magnetic field. Its field can be trillions of times stronger than Earth's magnetic field. Near a magnetar, magnetism is not a gentle compass force. It is a force of terrifying intensity. It could distort atoms. It could affect matter in ways impossible on Earth. It can power enormous bursts of X-rays and gamma rays. A magnetar is one of the clearest reminders that magnetic fields are not imaginary lines in a textbook. They are physical realities capable of storing and releasing colossal energy. A magnetar is a dead star where magnetism has become one of the dominant features of existence. If Earth's magnetic field is a shield and the Sun's magnetic field is a storm engine, then a magnetar's field is something almost mythic. A cosmic monster, made not of teeth or claws, but of invisible force. And yet it is governed by the same underlying electromagnetism that turns a compass needle. This is one of the most humbling ideas in science. The universe uses the same laws at wildly different scales. The same basic principles connect a refrigerator magnet, an electric motor, an aurora, a solar flare, and a magnetar. The scale changes, the strength changes, the consequences change, but the hidden language is related: moving charge, fields, forces, energy, loops, motion. Electromagnetism. The more we follow magnetism, the less it seems like a small topic. It becomes one of the deep patterns of reality. But there is one more layer to understand. Magnetism can seem mysterious because it often appears to act sideways. A magnetic field does not simply pull moving charges straight toward itself. A moving charged particle in a magnetic field can be deflected at right angles to its motion. Instead of speeding directly along the field, it may spiral around magnetic field lines. This is why charged particles can become trapped around planets. It is why Earth has radiation belts. It is why particles from the Sun can be guided toward the poles. It is why magnetic fields can shape streams of plasma into loops, arcs, and spirals. Magnetism is not just attraction and repulsion. It is motion guided into curves. It bends paths. It turns particles. It organizes plasma. It creates spirals, loops, and twisted structures. That is why magnetism appears so often in space, where much of the matter is ionized, electrically charged, and free to move. On Earth, we often think of matter as neutral: rocks, water, air, wood, metal. But in stars, nebulae, solar winds, and cosmic jets, matter is often plasma, a sea of charged particles. And charged particles respond strongly to electromagnetic fields. So in space, magnetism becomes architecture. It shapes the motion of matter. It stores energy. It draws invisible highways. It creates boundaries. It helps decide where particles go. This is why magnetic fields are so important in astronomy. They are hard to see directly, but they influence what we observe. They can polarize light. They can shape jets. They can influence cosmic rays. They can affect the behavior of gas around stars and galaxies. The universe is not only gravity. Gravity builds planets, stars, galaxies, and black holes. But electromagnetism shapes light, chemistry, plasma, technology, and much of the behavior of ordinary matter. Gravity holds Earth in orbit around the Sun. Electromagnetism lets the Sun shine as light that reaches our eyes. Gravity pulls matter together. Electromagnetism lets atoms form molecules, lets electrons bind to nuclei, lets chemistry happen, lets nerves fire, lets machines run, lets light travel. Magnetism is one part of that larger electromagnetic world, and yet it has its own strange personality. It feels hidden. It acts through space. It curls. It loops. It links electricity to motion. It turns invisible structure into visible effects. This is why magnetic fields feel mysterious even after we understand them. We can write equations for them. We can measure them. We can use them. We can build machines with them. But they still feel strange, because they remind us that reality is not limited to what our senses easily detect. A compass needle turns because Earth is wrapped in a field. A motor spins because current and magnetism interact. A generator produces electricity because motion changes magnetic conditions. An aurora glows because charged particles follow invisible paths. A solar flare erupts because magnetic fields twist and reconnect. A magnetar flashes because magnetic energy is stored in a dead star's extreme field. Everywhere we see the effects, not the field itself. The field is like a hidden hand, but not a hand with intention, a hidden law, a pattern written into space. Now return to the small magnet. Place it on a table. It seems quiet, almost humble, a simple object. But around it, space is organized, north and south, curving field lines, invisible influence, microscopic alignment inside matter, quantum properties of electrons, loops of magnetic force extending outward. Inside this small object is a doorway into the physics of the universe. A child can feel it. Two magnets snap together, two magnets push apart. The experience is simple enough for a child to notice, but deep enough for generations of scientists to study. That is the beauty of magnetism. It begins with wonder. Then it becomes technology. Then it becomes planetary science. Then solar physics. Then astrophysics. Then quantum theory. Then the nature of light itself, all from a force you cannot see. If we ask, how do magnetic fields actually work? The answer has many layers. At the simplest level, a magnetic field is an invisible region of influence around magnets and electric currents. At a deeper level, it is created by moving electric charges and by the magnetic properties of particles like electrons. At a technological level, it lets us build motors, generators, speakers, transformers, scanners, and countless machines. At a planetary level, it can form shields around worlds. At a stellar level, it can twist, reconnect, and unleash storms. At a cosmic level, it can shape plasma across vast distances. And at the most extreme level, it can dominate the environment around dead stars. But maybe the most important answer is this. A magnetic field is one of the ways the universe gives structure to empty space. It is an invisible pattern that tells charged matter how to move. It is a map of force, a memory of motion, a sign that space is active, not blank. When a magnet sits alone in a room, the room is not truly unchanged. The space around the magnet has structure. If a compass enters that space, it turns. If iron enters that space, it responds. If moving charge enters that space, its path bends. The field was there before the object revealed it. This idea appears again and again in physics. We often do not see the thing itself, we see what it does. We do not see gravity directly, we see falling bodies, orbits, tides, and curved paths. We do not see magnetic fields directly. We see compass needles, auroras, motors, particles, and light. Science often begins by noticing effects and asking what hidden structure could explain them. Magnetism is one of the oldest examples of that. Ancient people discovered lodestones, naturally magnetized minerals that could attract iron. Later, they learned that magnetized needles could point north and south. Compasses changed navigation, helping travelers cross oceans and map the world. For centuries, magnetism was mysterious, a strange property of certain stones, a practical tool, a puzzle. Then, electricity entered the story. Scientists discovered that electric current could move compass needles. Electricity made magnetism. Then changing magnetism made electricity. The two mysteries became one. From that unification came motors, generators, radio, power systems, and much of modern physics. The hidden field became one of humanity's most useful tools. And still, on a dark night, under auroras or stars, it remains wondrous. There is something deeply peaceful about magnetic fields. They are silent. They surround worlds without noise. They guide particles without visible paths. They hold patterns across space. They remind us that the universe is not only built from objects, but from relationships, a magnet and a piece of iron. Earth and the solar wind, the sun and its plasma, a neutron star and the space around it. A field is a relationship stretched through space. It is not a thing you hold, it is a way things can affect one another. That is why the idea feels so subtle. A field is invisible until something responds. A magnetic field is present before the compass turns. The compass does not create the field, it reveals it. In the same way, auroras reveal Earth's magnetic field. Solar flares reveal the sun's magnetic stress. Generators reveal induction. Motors reveal magnetic force. Magnetars reveal the extreme end of the same phenomenon. The universe is full of hidden maps. Magnetic fields are some of the most elegant. Now imagine Earth from space. A blue planet floating in darkness. Around it, invisible magnetic lines extend outward, compressed on the side facing the sun and stretched into a long tail on the night side. The solar wind flows past. Charged particles spiral. Some are trapped, some are deflected, some are guided toward the poles. Below, life continues unaware. Oceans move, clouds swirl, forests wreathe, cities glow, people sleep. Above them, an invisible shield is constantly interacting with particles from the sun. Most of the time, no one sees it. But in the polar sky, the shield sometimes speaks in light. Green curtains, red glows, purple edges, auroras moving softly across the night. The magnetic field becomes visible for a moment, then fades again into silence. Now imagine the sun. Magnetic loops rise from its surface like glowing arches. Dark sunspots mark regions of intense field. Plasma follows magnetic paths. Fields twist, energy builds. Lines break and reconnect. A flare erupts. A storm begins its journey through space. Days later, Earth's magnetic field trembles. Instruments record it. Auroras brighten. Satellites feel it. The connection crosses millions of kilometers. Invisible fields linking star and planet. Now imagine a magnetar, a dead star spinning in darkness. Its magnetic field is so strong that ordinary intuition fails. No compass could survive there. No atom would remain unaffected close enough to its surface. Magnetism, gentle on Earth, becomes cosmic violence. And yet the difference is not that magnetars use a different kind of magnetism. They use the same universe, only at an extreme. This is why magnetic fields are so fascinating. They are familiar and alien at the same time. They hold notes to refrigerators and shape disasters on stars. They power headphones and guide cosmic particles. They live in classroom experiments and in the most violent objects known. They are part of daily life, but also part of deep space. To understand magnetism is to understand that the universe is layered. The ordinary hides the extraordinary. A simple compass points toward a planet-sized dynamo. A fridge magnet points toward quantum behavior inside matter. A motor points toward the unity of electricity and magnetism. An aurora points toward Earth's relationship with the sun. A magnetar points toward the limits of matter and energy. Everything connects. The small and the cosmic are not separate. They are different expressions of the same laws. This is one reason science can feel so beautiful. A thing on a table can teach us about a star. A needle can teach us about a planet. A field line drawn by iron filings can help us imagine the invisible structure around worlds. The universe repeats patterns at different scales. Loops, fields, currents, motion, energy, matter responding to invisible order. As the night grows quiet, let the idea become simple again. A magnetic field is an invisible structure in space. It is created by moving electric charges and by the magnetic properties of matter. It can push, pull, twist, and guide. It can be weak or strong, stable or explosive, tiny or cosmic. It can hold metal to a door. It can spin a machine. It can protect a planet. It can light the sky. It can erupt from the sun. It can surround a dead star with unimaginable power. It is one of the universe's hidden forces made visible only by what it changes. And perhaps that is the most mysterious part. We live inside fields all the time. Gravity pulls us downward. Electric fields hold atoms together. Magnetic fields pass through the planet and through space around us. Light itself travels as electromagnetic waves. Reality is not just objects floating in emptiness. Reality is objects, fields, forces, motion, and hidden patterns. The space around you is not nothing. It is capable of carrying light, capable of holding fields, capable of guiding matter, capable of connecting one thing to another without touch. A magnet reminds us of this. It says, quietly, that the invisible can be real, the unseen can shape the seen, the empty can hold structure, and the smallest motion of charge can create a field that reaches outward into space. Tonight, somewhere on Earth, a compass needle is turning. Somewhere, an electric motor is spinning. Somewhere, a generator is producing power. Somewhere, an MRI machine is mapping the inside of a human body. Somewhere near the poles, particles from the sun are guided into the atmosphere, creating ribbons of light. Somewhere on the sun, magnetic fields are twisting. Somewhere in the galaxy, a magnetar waits in darkness, wrapped in a field beyond imagination. And all of it belongs to the same great story, the story of magnetism, the invisible architecture of force, the hidden map around matter, the silent field that shapes machines, planets, stars, and space itself. So the next time you see a magnet move without touching, or a compass turned toward north, or the northern lights glowing in the sky, remember that you are not seeing a trick. You are seeing the universe reveal one of its hidden structures, a field, silent, curved, invisible, real. And all around us,